Hey everybody, how's it going? Stoner Dave here, and I was just watching this video from a Detroit Wanker, and he's talking about a few things. First off, says he's going to make a distortion pedal. Can't wait to see that, given his reputation for amp building. I imagine it's going to be either something that he never does, or when he does do it, it's going to be just awful. But who knows? Maybe he'll get lucky. A distortion pedal is absolutely a easy build. I mean, it's really just an amplifier with a clipping circuit put on there. So, you know, be what it may be. But what I really want to talk about today is his discussion about resistance versus impedance. So, according to Detroit Wrecker, resistance is this. It's a resistor. That's all it is. It's a resistor. That's all it is. Anything else is impedance, right? Well, not exactly. It says impedance is a speaker, right? And if you measure a speaker, say a 4 ohm speaker, it should be rating about 2.4 ohms, according to Detroit Wrecker, or 2.6, something like that. He says if you measure an 8 ohm speaker and it reads 8 ohms, it's actually a 12 ohm speaker, which I've never seen a 12 ohm speaker. Typically, you see speakers as 4, 8, 16, and 32. Now, why is that? Those are powers of 2, right? Powers of 2 are easy to calculate when you pair them together, right? Because if they cut in half of 2 is 1, and 2 to the second power, so half 2 to the second power is 2 to the first power. 2 to the fourth power, half of that is 2 to the third power. So, it's real easy to do calculations based on powers of 2. So, there's that. But he says we measure the DC resistance of this, and this is a 4 ohm speaker. So, we measure the DC resistance on that. It should be 2.5 ohms or somewhere around there, according to Detroit Wanker. So let's take a look and see what we get when we measure the resistance across this 4 ohm speaker. It's rated 4 ohms. What do we have here? 3.5 ohms. Oh, 3.6 ohms. Very interesting. Now this is a 4 ohm, 3 watt speaker. What do we get when we measure across this? Looks like 3.2, 3.1. 3.2 now. So 3 ohms. This 8 ohm speaker, 15 watts. What do we get for our resistance across this? I can get these probes to stay on there. Well, stay on. I don't know if I'll be able to keep it on there. $7.3. Oh, 7.2. 7.1 now. So 7 ohms. Neat. It's another one, same rating. let's see here. Oh. Come on. Oh, keep losing my contact. 7.1. Oh, 7.0. No, 7.1, 7.1, 7 ohms. Fairly close there. This is an 8 ohm. A little tiny 8 ohm speaker, but 8 ohms. Should be easier for me to keep the leads on there. Oh no, this is a 4 ohm speaker. All right. Well, no, it's 8 ohms. This reads 8.4. Oh, 8.1. And okay, so got it to stop wiggling around 7.7 ohms. So, yeah, 7.7, basically 8. Now, I don't know why Detroit Wrecker is trying to tell people that these speaker resistances or impedances, whatever you want to say it, are going to be having different impedances or reading lower than what they actually are. I don't know why you'd say that. It doesn't make sense. But what I do know is that impedance is just alternating current resistance. So we take a resistor, we put an alternating current through it. That resistance is now an impedance. We take a capacitor, we put a direct current through it. No current will flow through it. Capacitors block direct current. Alternating current flows through it nice and freely. How freely really depends on the frequency. Frequency will determine impedance. That's why you don't have speakers that say a certain impedance on them. They say it in a resistance, because the resistance is the value that you're going to be matching to your system, whatever it is, whether it's an amplifier like your guitar amplifier or your car speakers amplifiers, your stereos, doesn't really matter. It's that resistance is what's going to be matched. They can't go by the impedance because they don't know the impedance. Impedance varies by frequency. And to demonstrate that, what I'm going to do is I'm going to run a signal through a couple of different components, right? So, got a capacitor, got an inductor, and I've got a resistor. Now, because we can't just measure straight across the component, right? Because we'll have either the full signal strength or ground on the other end. What we'll do is we'll put a resistor going from ground to the bottom of the component that we're going to be looking at. So we're going to be using a supposedly 5 volt peak to peak signal. I'm going to put a monitor on the top of the signal chain to measure the full strength of the signal, so we'll be able to see that incoming signal. Keep a good like that there. Alright. And we're using a, well, 10K right now. And I'm going to put a second probe going at the top of this reference resistor. And let's see, boop, boop, doo. All right, so I've got the signal going across the resistors first, and it's exactly what I expect. Let me pull up the camera here so you can see the oscilloscope and see what I'm talking about here. Okay, so here we have the signal. It's coming from this red probe, going into this first resistor, into this second resistor, down to our ground. Now we have our oscilloscope probe coming here to just measure this signal here. We also have a probe here at the center here, which should be approximately half the voltage. So on our incoming signal, I'm showing 5.0, between 5.0 and 5.04. And on our output, we have 2.24 volts. Here you can see the signal right here. Nice, exactly what you'd expect, you know. Little bit of fluctuation going on there, but that's because of a cheap function generator and not exactly the quietest room in here. But as you can see, as I adjust the frequency back and forth, we don't see any differences occurring in the signal. Back to our 10. And that's exactly what you'd expect. Frequency doesn't affect anything. It's got the same impedance at every frequency. It's a resistor. It resists. If I were to put a direct current going through here, which I can do, one moment here, I'll go ahead and set that up, I suppose. Okay, here's the same setup, same everything, but now with a direct current going through here. So this yellow line is set at 5 volts, as you can see, 5 volts per division, 5 volts for division, and it's approximately halfway between the two. Now, it's a noisy room. You can see a little bit of a fuzziness on the signal there. So nothing unusual there. The point is that it's behaving the same way, regardless of if it's DC or AC. It's a resistor. It resists. So, it's a resistor. AC or DC, it behaves the same. Signal is cut a little bit because, well, we're at a voltage divider. Blah, blah, blah. All right, so now let's take a look at the capacitor. All right, so for the capacitor, we're using it's 47 nanofarad, but it measures at 49.7 nanofarads. And of course, we got the same resistor here for our reference so that we can measure this away from ground and away from the signal. And we're using the same 5 volt signal. It's measuring about 4.92 volts peak to peak. And this is what it looks like. Now, the voltage peak to peak here of our signal is about 4.6 compared to the 4.9. Not a lot of impedance there, but some. Now let's see what happens as we increase the frequency. And you can see It went from 4.6, 4.8, 4.9. And as we get closer, it's going to get closer and closer to that 4.92 that we have on the input signal. And there it's showing up as being pretty damn close. It's, if you were to look there, see 4.92, 4.92, and this is at 81 kilohertz. Now let's see what happens as we go down in frequency. And we'll start going down a little bit slower. You can see, look at that. Now you can see there's a bit more impedance going on. You also notice that the signal's starting to go behind the peak rather than the peaks lining up like they did with the resistors. Very interesting. And the lower the frequency goes, the more impedance we seem to get. That is, the peak value is getting less and less the slower the signal goes. Now we're at 800 hertz, and the signal's really tiny. A few hundred millivolts, 760 approximately. You can see right there. Well, maybe you can't. Purple doesn't really show up that well on the camera. Sorry about that. But the incoming signal is still at 5 volts. Neat. Now let's see what happens when we put a direct current through there. All right, so we're putting a direct current, 5 volts going through there. You can see the signal going in, this yellow line, it's at 5 volts. 5 volts per division. See? Right there, 5 volts per division. One division, 5 volts. But this guy, he's right on 0. See, if I turn the signal off, yeah, 0. 5 volts. So the capacitor is blocking the DC voltage, but allows the AC to go through. Just the slower the frequency, the more impedance it offers. Now let's take a look at the inductor. All right, so here's the signal going through the inductor. Here's the inductor here. This is only 100 microhenries inductor. It's a very small inductor. So you won't really notice a big change in it until you get up to really high frequencies. So I've got a 60 megahertz frequency generator here, and I'm going at 10K right now. So not going to notice much of a change, but we're going to pump that frequency up quite a bit here, going by 10K at a time. Spread this out a bit. Like I said, it's a very small inductor. So there, we can start to see it now. I'm going to start going the frequency higher, 100K at a time. There, you can start seeing it. See, now you really start seeing it drop. And you'll notice that with the capacitor, the signal was going this way as we turned it up, is starting to go ahead of it. And this time it's starting to go behind it. Now it's going ahead of it. So that's kind of a key to impedance as well. See, we're at, what is this, 4 megahertz. And the signal is almost virtually gone. You know, I have to turn this up more so you can be able to see it. And you can actually see some of the noise in there now, pulsating through it. As we go more, oh, look at how much it's dropping. It's virtually gone. Oh, there, it's starting to come back. Oh, neat, huh? starts coming back because we get up to a high enough frequency that the internal capacitance of the inductor starts to do a little bit of work in there. It's kind of neat, you know, given what it is. But let's take a look and see what happens when we put a direct current going through this guy. All right, so you can see I haven't changed the position of the components. And here's the signal. Look at that. 5 volts, 5 volts, both of them. Now, the purple's is a little bit higher. That's just the way the generator, the scope does it so that you can see the two signals together. Very seldom does it put them directly on top of each other in such a way that you can't identify one from the other. But that's it. 5 volts. 5 volts and 5 volts. Why? Because there's very little DC resistance in an inductor. So, Detroit Wanker doesn't really know what the fuck he's talking about at all. You can say resistance or impedance. People will know what you're talking about, right? At least people in the know will know. Now, when you're talking about a speaker like this guy, and you say it's got 8 ohms, you can say 8 ohms of resistance because it does have 8 ohms of resistance, 8 ohms of DC resistance. And you say, well, it's impedance, it's impedance. Yeah, it is. What we've demonstrated, a resistor has the same amount of impedance as it has of resistance. They are the same thing. The only difference is we're talking about alternating current versus direct current. If somebody says, oh, this speaker has 8 ohms of resistance. Yeah, this speaker has 8 ohms. Well, not this one. This one has 4 ohms. But if somebody has an 8 ohm speaker like this one, so this speaker has 8 ohms of resistance, it has 8 ohms of resistance. Now, what about impedance, right? Because that's the big word of the day, impedance. Well, don't know if this speaker will be able to generate sound at 5 volts, but let's see what happens. That's an A, folks. Now, how much impedance is this speaker offering? It's registered at 8 ohms, and we measured it, I believe it was 7.4, 7.5. But what's the impedance of this guy? Well, there's a way to find out. So the way we would do that is we'd have to measure the inductance and the capacitance and what frequency we're operating at. So, first of all, we've got the resistance, but I'll measure that again just for fun. For shits and giggles, measure that on the LCR meter here. Let's see. Well, we're currently set up to measure microhenries, so we might as well do the inductance first. And we are showing 84.8 microhenries. 84.8. We'll just call it 85, make the math easier. See if I have a calculator here. I should have one pretty close by. Odd. I usually would have a calculator right here. Oh well. Guess we'll have to use the calculator on the computer here, so no biggie. Alright, so we have 85 times Now let's see what the capacitance is of this speaker. Should be pretty small. Because technically speaking, speakers have inductance, not really capacitance. Capacitance is kind of a byproduct of the loops going around. Yeah, it's showing negative capacitance, so capacitance is 0. Great. And plus 7.4. So altogether, at 440 hertz, this speaker offers 7.63 ohms of impedance. Now, without factoring in the inductive reactance, this guy has 7.4, 7.45. Now, let's see here. We can get the exact total amount right here. Seven point 7.3, essentially 8 ohms. And that's what it is. It's all a nominal number. All of these speakers, every single one of them, from your big ass speakers in your guitar amplifiers all the way down to these little guys that you'd find in different buzzers and toys. They all have a nominal impedance listed on them. It's nominal. It's the approximate impedance that you would see on it. And how do they determine it? They measure the DC resistance. That's it. They just measure the DC resistance. There's no other calculations that go into determining this impedance. Now, you can't really measure the impedance of a device unless you're running a function generator through it and you're measuring the voltage drop across it. Just for fun, I'm gonna plug this 440 hertz through this speaker and see how it sounds. And you'll notice I'm not really paying attention to a positive or negative terminal on the speaker because it doesn't fucking matter. Oh, you can barely even hear that. This is 60 hertz. There's 50, 40, 30, 20, 10, and none. So, a lot of people don't understand this because it's not something that you're taught in school. The way these speakers work is very similar to the way your guitar pickups work. See, if you were to look inside here, hope you can see inside there. Right there, you see the, looks like little rings. Those are coils. Coils are an inductor. That's all it is. It's a big inductor. An inductor big enough to have 8 ohms of resistance. Your guitar pickup has an inductor that's like 56,000 ohms of resistance, 60, sometimes 80, depending on what kind of a pickup you have, But all of that impedance is just because of how much wire is being used to make these coils. So you'll notice there's a big magnet on the bottom of the speaker here, right? So what happens is as an electric current goes through these coils, it generates a magnetic field, right? That's why you don't want to hook up a battery to your speaker. I know there's a guy, Scott Grove, in one of his videos said that if you want to know which way you plug your speaker in to hook a battery up to it, he said take a 9-volt battery and do that. And that's about the worst thing you could do to a speaker, because 9 volts of DC is going to just pop this out or pull it in, depending on which way you plug it in. And you don't want to do that. But as the current is going through, one way it has a magnetic field that's got the same polarity as this, so it pushes away. And the other way, it has a magnetic field that pulls towards this. So this coil here gets pushed and pulled up and down as this changing current is going through it. That coil is attached to this cone of paper, which, yeah, it's just paper. And this pushes and pulls it up, vibrates the air. That's the sound that you hear. It's very simple, but not a lot of people understand that. It's the whole reason why there's a magnet on the back of your speaker, and every speaker has a magnet. Some have really big magnets, some have small magnets, some have weird shaped magnets. Some have smaller magnets. Some have magnets that are almost as big as the speaker itself. But they all do the same thing. these coils, electricity going through them, generates a magnetic field, and they push and pull against this magnet to move the speaker. It's amazing, right? Even these headphones here, you know there's 32 ohms in the coils in these speakers? It's a little tiny speaker in here, a little tiny magnet, and all those little coils of wire. 32 ohms. Crazy, right? But yeah, that's the deal with impedance versus resistance. So again, can somebody say, oh, it's got impedance or it's got resistance interchangeably? For sure. The units are ohms. Ohms is resistance. Ohms is impedance. Impedance and resistance are basically the same thing. When you say impedance, you are speaking explicitly about alternating currents, not about speakers. Speakers have nothing to do with it. I mean, think about this. You talk about your pickups. You say they have 56K of resistance. It's actually impedance. It's actually impedance. You say your guitar has a output resistance of 10K, 100K, 200K. No, it's actually impedance. Typically, when somebody says output, they say output impedance, input impedance. And whether you're dealing with AC or DC, it's just the vernacular of it. You'll say impedance because it's input and output impedance. But when you're just talking about a component like a speaker or a resistor, you'll talk about its resistance. When you're talking about components like capacitors and inductors, you don't typically talk about their resistance or impedance because you talk about their capacitance and their inductance. The amount of impedance and or resistance that they offer is usually determined by those factors, you know? Like a capacitor, like this capacitor right here. I put it in, I measure it, right? I say, oh, it's about 50 nanofarads, 49.2. About 50 nanofarads. Now, how much impedance is that? Now, to figure that out, well, we'd need to have our calculator. And for some reason, I can't seem to find mine. But what the hell? I think that's enough zeros. Hit equal too many times. Let's try that again. 1 over. All right. So, for the amount of impedance that this capacitor offers at 440 hertz, we have 0.00138230076758, and it keeps going and going and going because pi is a factor of this equation. But it's still next to nothing. And you can see it on the scope when I ran the current through there. Yeah. Direct current, this thing is infinite impedance for a direct current. That's a frequency of 0. Now, you typically refer to that as resistance, right? But no. Now, there's another factor. It's called the ESR. ESR is equivalent series resistance. And that one, I'll leave it up to you to try to figure out. What is the ESR of this capacitor? All right. Well, I think I've talked enough about this. Hopefully, even somebody as dumb as Detroit Wanker will be able to figure out what he's talking about after watching this, but I highly doubt it. He'll probably still be talking about speaker impedance and think that that's actually a thing. And while it is, it's not that big of a deal, right? Because like I just showed you, we can measure the resistance of the speaker, and we see that the resistance is the same as the impedance, essentially. So why try to convolute things by saying, oh, you can't refer to speaker's resistance, but we measure it with its resistance? And why would you say that a 4 ohm speaker is going to be reading at 2 ohms when it's going to be reading closer to 4? I mean, yeah, it might be reading, well, let's see. According to this is a 4 ohm speaker. Let's see what the resistance is of this. I'm going to just hook it onto the clips here. Five 5.5. Look at that. It's going between 5.4, 5.5, 5.5. Because it's nominal. It's an approximation, but it's approximately 4 ohms. You can see it right here on the back. And just if you're curious where this speaker comes from, it's actually from a computer speaker. So you gotta wonder, where do these people come up with this shit? Why did they come up with this shit? What are they hoping to accomplish by making up things that are clearly, provably wrong? Flip off this extra bit of wire on this. it just doesn't make sense, right? I mean, I could understand if you were making up something that was funny, or laughable, or even if it was just something that couldn't quite easily be verified as wrong, right? Like if it wasn't so easy to prove that he was wrong about everything he said about impedance and resistance, I probably wouldn't have done it. But it's very easy to prove wrong, like I've just done. So, do resistors have impedance? Yes. Do speakers have resistance? Yes. Is there a difference between resistance and impedance? Not really. I mean, the only real difference is that when you're talking about impedance, you're including other factors besides just the resistance. You're talking about stuff called reactance. Now, the really big difference about this is power consumption, right? So you run a current through a resistor. Power is dissipated across the resistor. Real power is dissipated across the resistor. And you can feel this as heat given off. When you're going across the resistor, though, or the capacitor, you don't see that heat coming off of it. There's not. It's not really dissipating power. There's what's called apparent power loss. So you could think of this like if you say you get a fountain drink, like you go to Circle K and you get a big gulp. I guess that's a 7-Eleven. You go get a soda out of the fountain. You fill it up, and you fill it up all the way to the top, and there's like this much foam on there, right? Soda and foam. The soda is the actual amount that you can drink. But it appears that you have the full glass. That top bit is apparent soda. Well, the capacitor has the same thing going on, right? You look at the signal loss, you see there's a voltage drop across it. But it's not really dissipating power. It just appears to be dissipating power. It's apparent power. Same thing happens with an inductor. I mean, an inductor does have a bit of resistance to it, so it's not quite as easy to look at it there, because you start putting enough juice through an inductor, it'll start getting a bit warm, but not as warm as what it would appear to be, because you start seeing this voltage drop across it, and you'd imagine that it'd be getting a lot hotter than what it is, but it's not, because it's just an apparent power loss. That's it. This right here is often referred to as an RF choke. So you notice that at low frequencies it wasn't really doing much, but as we got up into higher and higher frequencies, it really started to have some drop. You get into what's known as the radio frequency range. This guy starts actually showing some drop to it. But it's not real. It's apparent. There's a what's called a J factor that goes into these guys, and that's based on the impedance. Not the resistance, but the impedance. As I said, this guy right here, as far as resistance is concerned, he's only got a little over a quarter of an ohm. He's going between 0.3 and 0.4 ohms. So it's almost half an ohm, but more than a quarter. So it's right in between there. Say 3.5. Not a lot of resistance, but you get to a high enough frequency, he's got a great deal of impedance. But again, yeah, I'm really looking forward to Detroit Wanker's distortion pedal. I gotta ask, what op amp are you planning on using for your distortion pedal? I've got quite a few to choose from, and you seem to think that you're going to put out this tremendous sounding distortion pedal. So I'm anxious to hear it. I won't post my video until after you post yours, but I am very anxious to hear all about your tremendous pedal making abilities. Because I have a feeling that, I have a feeling you're going to fail at it, is what I have a feeling. There are a lot of schematics available for the pedals, though. If you want to cheat and make somebody else's pedal. But you seem to think that you know what it takes to make a great, better sounding pedal than anybody could make. So I really look forward to seeing your pedal design that you're going to make, that's not going to be just a Tube Screamer clone or an MXR clone or some other pedal out there that's already been done to death. Because I tell you, there are a lot of Tube Screamer clones out there. There are a lot of MXR copies out there. Please, do something original. I beg you. All right. Well, that's enough from me. Thanks for watching. Hope to hear from you soon. Have a great day.